We are the Aachen Drone Development Initiative, a student association at the Technical University of Aachen, bound together by our shared passion for aerospace engineering. Our goals are the participation at international competitions like the Air Cargo Challenge and the development of civil UAV solutions with companies. We have our main workshop in Aachen, right at our university's main building. Here we develop and build a wide range of UAVs like model planes, autonomous multicopter and airships. A short walk away we have our composite materials workshop. Here's where many structural carbon and glass fiber components of our aircraft were built. We organized our teamwork in a weekly online meeting, during which we reported results of the last week, discussed design decisions, and planned the upcoming task for the next week. Each team member was always free to choose their task, and more experienced team members would take the lead on complex tasks. Our aircraft's design is based on the software that was written by our team leader Henry Schmidt as part of his bachelor thesis. This software aims to create a preliminary aircraft design. It uses the rules of the Air Cargo Challenge as restraints and its scoring system to evaluate and optimize the design. To improve the assumptions that had to be made when writing the software, we did a number of tests. For this, we used the facilities of our university as well as building our own equipment. The software creates a basic aircraft design in multiple steps. Each step builds on the results of the previous one, and hundreds of design variations are evaluated in each step. At first, a conceptual design is created. The type and size of battery are chosen, and a simple wing design is created. This very rudimentary design serves as the basis for the following steps, which will improve the design by modeling the wing at finer detail and optimizing the airfoil along the wing. After the last step of optimization, we had a basic aircraft design, as well as predictions for data like the maximum payload capacity, takeoff speed, and others. From this, we had to design a suitable fuselage, and to determine its size, we modeled the blood bags that would be used in the competition and arranged them in different ways until we found a good configuration. To this, we added the major electronic components and modeled a fuselage that could accommodate all of those. We chose to build the fuselage out of carbon and glass fiber. For this, we would need molds, which we printed in segments using our 3D printer. These segments were then glued together, and we used a spray-on putty to cover the uneven surface from the 3D printer. This was then sanded and polished. From these molds, we were able to build many parts, which was great for our prototyping. The fuselage consists mostly out of carbon fiber. Only at the front we used glass fiber, since carbon fiber blocks radio communications. The outer skin is reinforced with composite ribs. They also act as dividers for the cargo bay, securing the payload during flight. The main gear's mount is made out of plywood, which we cut using our CNC router and include into the fuselage, with additional reinforcement. Up at the front, we used a similar wooden reinforcement for the nose gear. It also acts as a mounting surface for our batteries. The nose gear is machined from solid carbon fiber and held between two plates which are glued to the fuselage. Both the nose and the main gear can easily be removed. The main wing was our biggest challenge. We chose to go with a similar approach as we did with the fuselage, with the major difference being that the skin of the wing would be made out of a carbon fiber and foam sandwich. First, we tried the same method of 3D printing the molds that we used for the fuselage, but this failed because the molds were too weak to withstand the pressure of the vacuum bag, which we needed for the lamination of the wing. After this failed attempt, we decided to use our CNC router to machine a new set of molds. These molds would be of much better quality and stronger than the 3D printed ones. We decided to use MDF for the molds. It can easily be machined, but it's too soft to be used as a mold as it is. To strengthen its surface, we soaked it in epoxy resin. The cured epoxy resin makes a very hard surface, which we could now machine to its final dimension and then polish. Another advantage of this method is that mistakes can easily be repaired and the mold blank can be reused after a failed attempt, which was very useful since we were forced to start over many times after running into various problems. One big cause for trouble was our CNC router, which was simply not up to the task of operating for up to 5 hours continuously, and had to be upgraded in various ways. We eventually were able to machine all 4 molds, and the first attempt at laminating a wing showed that the molds were working fine. But at this point we had not enough time left to work on the difficult process of laminating these composite wings. As an alternative, we decided to build the main wing in the foam core process, which we used many times in the past. We used a hot wire and templates to cut the foam core of the wing in multiple segments. The segments were then glued together and sanded. We then added the pockets that would hold the wing spar, as well as wires and mounts for the servos. To give the wing its strength, we covered it with carbon fiber cloth. The carbon fiber was first soaked in epoxy resin and then cut to size. A strip of aramid was added to the lower side of the wing. This would later serve as the hinge for the flaps and aileron. This layer was then put on the foam core and sandwiched between 2 plastic sheets. The wing was then cured in a vacuum bag. The vacuum ensures a good contact between the carbon fiber and the foam core, and the smooth surface of the plastic sheet is copied to the wing. The wings are connected to each other by a carbon fiber spar, which is made out of 2 10mm carbon fiber tubes and has a dihedral of 2 degrees. Its purpose is to resist the momentum load on the wing during flight. The fuselage is connected to the wing by 4 steel pins, which also transfer the lift force from the wing to the body. The main body of the fuselage does not extend all the way to the empennage. About 1/3 is covered by a carbon fiber tube, to which the elevator and rudder are mounted. To mount the tail, the tube is simply pushed into the fuselage, and the friction and some tape are enough to hold it in place. The interesting shape of the elevator is the result of our software, which tried to optimize the effectiveness of the elevator inside the size restriction imposed by the competition. The elevator and rudder are both made using the same foam core method we used for the main wing. The main flight of our aircraft went by without any problems. The plane flew for about 2 minutes and behaved well in all flight situations.